Okay, uh, hi, welcome to my channel, and today we are going to talk about the potential well problem, particularly the one-dimensional potential well problem. Here, let me start with one dimension. This is a 1D potential well problem. This is a very common basic problem that you can see in quantum mechanics. Okay, so we remember the time independent Schrödinger equation. This is written as minus h bar square, which is the reduced Planck constant, by 2m del square psi, which is the wave function, del x square plus v psi equals to e psi, and psi here is a function of x and x only, because we are just considering the x-axis. Okay, so to start with this problem, let me reduce the size of my pen. Okay, yeah. So to start with this problem, we need to first see what is a potential well, or what is a one-dimensional potential well. Now consider this as your x-axis, and your potential is increasing in this direction. Now between 2 points at x equals to 0 and at point x equals to L, suppose we choose 2 points, this total distance is L in x-axis, this is x-axis. The potential that is forming between this is 0, which means a particle can roam around freely in between these balls, but with a boundary condition at x equals to 0 and x equals to L. At this boundary beyond x equals to 0, like not beyond, lesser than x equals to 0, we have v as infinite. Classically, this says that it is a impenetrable wall and particle can't penetrate this wall. That's why it is taken as v is equals to infinite. It is an infinite potential. Similarly, x greater than L, here in this direction we have v greater than infinity. So this is the basic problem. We have our two boundary conditions, and with these two boundary conditions we are going to solve this particular well. How are we going to solve this? The first step is to write the equation. X is taken because it's in x-axis. Now, as we have seen, inside x equals to 0 and x equals to L, v of x is equals to 0. V which is not a function of x exactly, v is 0. Or you can say v is a function of x, as v is increasing with x, but let me write it as v equals to 0. So for this purpose, we can write this particular equation as, let me erase this, minus h bar square by 2m del square psi plus del x square equals to cell, and rearranging both the sides and bringing it just to one side, we will have del square psi by del x squared plus 2me by h bar square psi equals to 0. This is similar to a harmonic equation problem. Del square, suppose a by del b square plus k square equals to 0. Because these two have similarity or a simple harmonic motion or a harmonic equation particularly. So that's why they have very this total can be considered as k square, or we can write this as k square as 2me by h bar square, or E is equals to h bar square k square by 2m, which is also p square by 2m. P is your momentum. Yeah, P is your mom. Anyway, so let's start this. Now, this particular equation that we have in our hand, it looks like this: del square psi del x square plus k square psi equals to 0. And this has a very generalized solution. This particular harmonic equation has a very generalized solution, and this generalized solution can be written as psi as a basic function of x is equals to a sine k of x plus b cos k of x. Brackets. Yeah. Okay. So you can solve this equation by taking a double derivative, and you will get to this position only. Anyway, so let's remove this and let's just write our generalized solution: a sine kx plus b cos kx. Okay, so now taking the first boundary condition, psi of x at x equals to 0 is 0, because there is no wave function that is penetrating at that particular point, and psi of x equals to a is also equals to 0, or x equals to L. In our case, it's taken as L. A, L, whatever you can say. Anyway, so by putting these two conditions, suppose for the first condition we put psi x equals to 0, we have a multiplied with 0 because sine of 0 is 0, plus b multiplied with cos of 0. Now, cos of 0 is not, it doesn't give us 0, but b can give us 0, so we can put this constant equals to 0. Finally, after putting that in our generalized solution, we have psi of x is equals to a sine kx from the first boundary condition, by putting the first boundary condition. Now, starting from that point, let us put x equals to L equals to a sine k L, which is equals to 0, or which is also equals to sine of n pi for n equals to 0, 1, 2, and so on. So we can write, equating the previous, KL is equals to n pi for n equals to 0, 1 and so on, n being a whole number, and so we finally get k is equals to n pi by l, right? Or we can write psi of x is equals to a sine of n pi by l into x. Now the last unknown term is this. With this we can find out by finding out the probability density. Probability density is given by minus infinity to infinity. Psi star psi is equals to 1, which means if we consider a range of, suppose this is considered as x equals to minus infinity, x equals to positive infinity. So in the one axis we can find the particle here, 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 and the entire particle summing all the probabilities of, suppose the particle is here, suppose the particle is here, or anywhere, suppose the particle is here, 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 and summing up all the probabilities, it should always amount to 1. That is your probability density. But in this case, our probability density has been reduced to x equals to 0 to x equals to L. So we don't have to consider the entire length, because in this the probability of finding a particle has been nullified. So our range starts from 0 to L. A, because we are putting psi star, sine, not k, is sine n pi L x multiplied with the same, because it's psi star psi and there is no imaginary factor, so we can write it as sine square a square, this whole equal to 1, or a square 0 to L 1 minus, using this identity, I will show you that identity, cos of 2 n pi by L x dx. Oh, I forgot that. dx, we have to write dx. So whole equal to 1, this whole divided by 2. Because this is a cos function, and if you can see, if we integrate it, it will form a sine function. So this can be further written as 2 separate integrals minus of, as it is a cos, it becomes sine of 2 n pi L, 2 n pi L x from 0 to L by 2 multiplied by 2 n pi L. The entire a constants comes down. Anyway, so in this case, if we put x equals to 0, we don't have to put n, we can start n from 1. So if you put x equals to 0, so this entire terms becomes 0, and if you put x equals to L, the entire terms again becomes 0, so this entire term goes to 0. So we are just left with the first term. So we can write this as a square a by 2 equals to 1, which gives you a is equals to root 2a. Finally, we can write psi of x equals to root by 2a sine of n pi l x. That's your final form that you have derived. Thank you. If you like this video, if you find the explanations okay, please give your comments, and I would love to read them. And please also provide your valuable likes, comments, and please subscribe. Please do that. Thank you.